could be for a living person. Snack. Headline here.
Ready anytime.
You guys will survive.
What's that? Anytime.
Oh, yeah, that's right. Yeah, burns everything.
Okay, good afternoon. It's my great pleasure to introduce today's colloquium speaker, Professor Daniel Chavas. He's an associate professor in the Department of Atmospheric and Earth, Atmospheric and Planetary Sciences at Purdue University. His research focuses on the physics of extreme weather, particularly hurricanes and tornadoes, as well as other severe storms, their dependence on climate, and the application of this knowledge to risk analysis. His research methods include the use of idealized numerical models and observations while delving into the theoretical underpinnings of how these weather systems work. I've known Dan since about 2005 when he was a student in our department and began working in my lab on a project studying African easterly waves. I do have just one quick picture I'll take the pleasure of during this introduction, if it comes up. Check one on. So, you know, these memes. So this is how it started back in about 2006 or 7. This may have been just before Dan left. And then here's how it's going, I guess you could say. And people notice that there's the same elements are on this. Anyway. So, yeah, Dan earned his bachelor's science degree in our department as well as in applied mathematics in 2007 and earned his PhD at MIT in 2013. Before he started at Purdue, he was an NSF postdoctoral research fellow in civil environmental engineering at Princeton University. Thank you again for your visit today. It's really, we're really delighted to have you here, and we look forward to your talk, Tropical Cyclones on the Rotating Sphere. So welcome.
Thanks, Michael. Thanks everyone for coming. This is really awesome. I've been back here in forever. It's really cool to be here, be in the building, be in this room, which I literally forgot what it looked like until we got down here. So yeah, it's an honor to be back and talk about some of the things that I work on now, which definitely has been built on things that I learned when I was an undergrad here many years ago now. So yeah, I'm going to talk about tropical cyclones on the rotating sphere. Hopefully you'll have a sense of what that means moving forward. I'll come back to this pretty animation here, but it's just a beautiful movie of, from 2017 with multiple hurricanes in the Atlantic Ocean. So I want to have a quick intro about myself as a person, because it actually, I think, informs a little bit about how I think about the science that I do. So this is a picture of me not on this date, but when I was little, and on June 2nd, 1990, I don't know if anybody here remembers that day and time. We are here in Madison. These blue crosses are high wind reports from the Storm Prediction Center. And so on this day, when I was 4 years old, a tree fell on my house. And it was very loud and traumatizing, and it terrified me into loving the weather. So this is, and my good friend Quentin is in the audience, who's known me since then, which is awesome. So yeah, so this event got me into the weather, and actually ever since then, I only found this out a few years ago. It turns out this is all these red dots here in Indiana, so I'm at Purdue. This is actually still the single largest tornado outbreak in Indiana history. It happened on this day. So sort of a strange coincidence here. We just had high wind. So, okay, so there's the tornado. So yeah, so my background, so here at Wisconsin, my undergrad was really in weather forecasting, meteorology, which was awesome. I went to grad school at MIT, which was a climate program, and I found out very quickly how different those worlds are and how much, to some degree, people don't even seem to speak the same language in terms of how we think about the world. And then I did a postdoc at Princeton, which was actually in civil and environmental engineering, and I got to learn all about risk and probability and statistics, which I use today. And then since 2016, I've been at Purdue. So I try to I integrate all of the knowledge across these different experiences. And so in particular, I mentioned I tend to work kind of in between weather and climate. And so sometimes I feel like I kind of fall through the cracks. between the two communities, but I'm often trying to have background in both, and so I'm really trying to bridge that gap of thinking about weather in the context of climate. So briefly, so this is my awesome lab group. So I'm going to talk about tropical cyclones here. I do a whole bunch of different things. So I should say hurricane, tropical cyclone, the same term. So I'm not going to read through all these, but I work on the inner structure and dynamics of a hurricane in various contexts. I work on hurricanes in the climate system. So why does the climate system produce hurricanes, where it does, and then I've more recently been working on severe thunderstorms, and again, thinking from the climate side of things of how simple questions like why do we have severe thunderstorms or tornadoes at all on our planet. So if anything jumps out to you here that you're interested in that I won't talk about here, I'm happy to talk about it separately. So yeah. There we go. Oh, yeah, and so, and generally, again, I work across theory, modeling, and observations, so try to integrate all three of those as best as I can. So kind of at a broader level, I mentioned that, I'm between weather and climate, and so how I think about weather is that we often think that weather is hard to predict, which is definitely true, but it is definitely not random. So the weather, the types of phenomena that we have in our atmosphere is really highly organized in space and time by the physics of the climate system. So that's how I think about things. So for example, that we have hurricanes over oceans at low latitudes in our present day climate state. And so you can see them in our movie here. So here's Hurricane Irma, Hurricane Jose, we have Katia, again, this is from 2017. And this is a geostationary view looking down from space. So you're seeing, this is visible satellite switching to infrared at night. So you're seeing the cloud tops though, essentially. And then on top of that, so we don't have them at this time, but severe thunderstorms I mentioned, they're common over North America, over Central South America, and a few other regions around the world. And so a lot of my interests are in understanding why that is, that these types of phenomena occur in specific regions on Earth. And, okay, so yeah, so what about the climate system generates these phenomena? So this is a kind of a central underlying question of my research. And so on top of that is when I look at this is beautiful. We all many of you probably spend a lot of time looking at satellite imagery of our atmosphere, and you see what is both beautiful and incredibly complicated at the same time. There are so many different, in very simple words, blobs and swirls and linear bands of clouds all over the place, all happening at exactly the same time. And so in some sense, if we want to be able to understand one thing in this system, it would help to be able to deconstruct our climate system, to be able to focus on the thing that we care about and try to remove the things that we don't necessarily care about. So that's something that underlies a lot of what I do. And so what I'm going to do is, let's see here. Oh, I'm missing a slide. Okay, so I'm going to talk a little bit about hurricanes on a sphere. And there's going to be three parts to this. And so I'm going to focus first on this work that's from a paper that we published a couple of years ago on fundamental dynamical controls of hurricanes on the rotating sphere. So this is work done with my colleague Kevin Reed. And then there's going to be a couple of other components that I'm going to touch on related to the size of hurricanes that came out of this work. So let's do a little bit of an intro on hurricanes. So this is a map of the colors. So the grays are the continents, the colors are sea surface temperatures, and this is just a really nice map this is average from 2000 to 2008 of the average sea surface temperatures globally. And then the green dots here are genesis points for tropical cyclones, for hurricanes, and then the black lines are the tracks that tropical cyclones follow. And so I put up here is that hurricanes on Earth are thermodynamically confined to the tropics, which is to say that when you go to higher latitudes, the sea surface temperatures get colder, so the colors go from red to blue. They also run into the jet stream, which is something that effectively, one way to think about it is they tear them apart, but they also energetically act to destroy a tropical cyclone. So when you go to higher latitudes, you'll notice the tracks tend to stop as you approach the colder waters, or also if they go over land. So in this way, then thermodynamically, we have tropical cyclones confined within a tropical band on our planet. So I'll highlight boxes around here. You'll notice that if you look specifically at the equator, you don't almost never have a tropical cyclone or hurricane at the equator, which is something I'm going to touch on. So they're confined within the tropics, but also a little bit off of the equator at least. And so that's something we'd love to understand, is what controls that. And so, yeah, so a lot of work up till now has focused on thermodynamic understanding of tropical cyclones. So we know that hurricanes, they like to form over warmer water, and there's a lot of detailed thermodynamic theory that goes along with that. But our understanding of the dynamical controls of tropical cyclones is much less well understood. And so that was a focus of our work here. So what are the fundamental dynamical controls of hurricanes on an Earth-like planet, which is a way to say a rotating sphere that has a thin atmosphere on top of it, like we live in. So I'm going to first tell you a little bit about the questions that we want to answer, and then I'm going to talk through the methodology, and then we're going to try to answer these questions. So there's 3 questions. One is, what controls the genesis rate versus latitude, which is really hard to deduce observationally, because most of our tropical cyclones where they form is a relatively narrow latitude band. Second is, I mentioned, they don't form on the equator, but we'd love to know, well, so if they don't form on the equator, how far off the equator do you need to be? So we'd love to know that. And then the third question is, what controls the size of a storm and how that varies with latitude? And so I'm going to come back to these each individually as we come along. But a key thing I want to say is that across all these, when I talk about dynamics, the first thing that hopefully might come to mind is the Coriolis parameter, F. So the prevailing hypotheses at the time for all of these questions was something to do with F. And I'm not going to dig into the details on that in this talk, but just that they all somehow, the expectation was that they would depend on F. And so we'd like to test those hypotheses, see if maybe they're right, or if they're wrong, if we can come up with something different. So let's think about this, and let's zoom out and think about what it means to talk about planetary dynamical controls for circulations in our atmosphere, we can say. So here's our rotating Earth. So when I think about this, you can think about planetary thermodynamic forcing that comes from the fact that we are a sphere going around a star. So we have large-scale gradients in incoming solar radiation, so solar insolation at the top of the atmosphere. So we get more solar insolation at low latitudes than at high latitudes because of the geometry of our planet. And then on top of that, we also have differences in the things that absorb solar radiation, including things like land versus ocean. So we have surface variability, and there's much more in there as well, but kind of large-scale features that govern thermodynamic variability that can force motions in our atmosphere, let's say. So superimposed on top of that then is planetary dynamical forcing. So this is our Coriolis parameter that hopefully many of you love. 2 times the planetary rotation rate times the sine of the latitude. It's 0 at the equator, and twice the planetary rotation rate at the pole, so a maximum at the pole. And so what we'd like to do, ideally, if I could, is if I'm interested in the dynamical controls of things on our planet, we'd love to be able to remove this thermodynamic forcing. And so we're going to try to do that. But so let's first think through this dynamical forcing. So we'd like to isolate dynamical controls. So now we have our rotating sphere. We're just thinking about F. And so how are we going to do this? How can we isolate these dynamical controls? And so what we can do is, one thing that I think is amazing is, this is output from a climate model for the historical period. This is from 1979 to 2012 of our recent climate. And so one thing I find amazing is that we have these models that we mostly focus on the reasons that the models have biases or have problems in representing features in our atmosphere. But what amazes me is that to first order, it does a remarkable job of getting the phenomena where we expect them when we expect them on Earth. So the colors here are the near surface wind speed. And so here's the Atlantic. this is in the northern hemisphere summer at this time. We're getting hurricanes that are forming. So you can get another one. And it generally puts hurricanes where we expect them over low latitude oceans, in the places we expect them and the months of the year that we expect them on Earth. So here's a few more of them again. So these little circles are these little tropical cyclone-like vortices. So that's really awesome because what it means is that we have a model that we can use to understand or simulate the real world, but then we can also use it as an experimental testing ground to do other things with them. And so we can do something, we can change our planet in a way that will look something like this, which looks totally different. And so this is a world where you're seeing now only tropical cyclones. So each of these little circles here are tropical cyclones. So this is a world where what we've done is taken out, it's an aquaplanet, we've removed land, and we've set the ocean temperature to be constant everywhere on the planet. So we now no longer have large-scale temperature differences. And then on top of that, although this matters less, is we make the solar insolation constant everywhere on the planet too. So, which is something that is not physically possible, but is doable in a model. So a sphere going around a star can't have the sun shine the same everywhere. But we don't care because it's a computer model, so we can do things, do experiments that we want because we want to. And so in this world, so this is this aquaplanet with uniform thermal forcing, what you've done is by removing large-scale temperature differences, so again, the SSTs are uniform everywhere, you've removed the ingredients that give you, say, a jet stream, give you baroclinic instability, so extratropical cyclones, and basically all of the ingredients, or the ingredients that you need for most other phenomena that exist in our atmosphere, and what's left over are tropical cyclones. And so what you'll notice is, you look at this and you say, this looks nothing like the real world, and so there's tropical cyclones that are piling up at high latitudes, but if you watch closely, you'll notice that they actually form at low latitudes. Let's see if we can get one here, and they move poleward and westward with time, which is what tropical cyclones, I should have emphasized that in the plot before, that tropical cyclones tend to move poleward and westward with time. But instead of running into land or running into the jet stream or running over cold water and then dying, none of those things are in here that kill hurricanes. And so what they do is they just keep going and they sort of pile up at high latitudes. And every once in a while, if you watch them, you'll see a couple of them merge together, which I think is the primary sink of tropical cyclones in this system. And so what I want to just zoom out for a second is if you look at this movie, what you'll notice is it's sort of like a sandwich of a cyclone-filled polar cap, or maybe a hamburger, with two cyclone-filled polar caps sandwiching a cyclone-sparse equatorial belt. So that's to give it like a broad view of how you would describe this world. So hopefully it'll convince you that this world is actually useful to understand our real Earth, even though it looks nothing like the real Earth. Okay, so we'll come back to that. So I want to come back to our planetary dynamical forcing here, our F. So if you want to think about this as F, when we're talking about a hurricane, it's a rotating system. It needs a source of rotation, and that source is ultimately the rotation of the Earth itself. So F is the planetary vorticity, and so that is ultimately, you can think of F as the source of rotation. But that's not the only way in which F is dynamical forcing. So on top of that, F varies with latitude, and so that gives us what we call beta, which is just the meridional gradient of F, 2 omega over a cosine of phi. And I'll just emphasize here that F is a minimum at the equator and a maximum at the pole, and beta is the opposite. It is a minimum at the pole and a maximum at the equator, which would be important. So why do we care about beta? Is anyone out here? Where does beta show up? What does beta give us? Rossby waves, all right. So Rossby waves. So beta is our source of Rossby waves, which we've all learned and grown to love, and it's going to turn out that we haven't thought enough about Rossby waves somehow, but we're going to come back to that. So yeah, so beta is our source of Rossby waves, and that's really important. So there's two ways in which having a rotating sphere matters dynamically, and you can think about it in terms of the parameters as F and beta. So F and then the gradient of F, and how those vary with latitude. Okay, so what I'm going to put forth, here is really a basic theory that I'm just going to kind of assert, and then we're going to talk through of thinking about this system, or this aquaplanet with uniform thermal forcing, in the context of two length scales. So we have a world that has lots of tropical cyclones, And so here, this plot is latitude on the x-axis. You can think of it north or south, and the y-axis is a length scale. And so there's a natural length scale for tropical cyclones that I'll just call L sub f, which is a 1/f length scale. So that may look like a deformation radius to some of you. And it's not super important, the distinction, but for tropical cyclones, there's actually a different, instead of a gravity wave phase speed in the numerator, we have a velocity scale that's the potential intensity that is important for tropical cyclone theory. So, but the key thing here is not that. That's something what's nice is this is constant, approximately constant in simulations. But it's this 1/f scaling that gives you something that blows up as you go to the equator and then decreases as you go. It decreases rapidly as you go towards the poles. So superimposed on this is another length scale that you may or may not have learned before. That's called the Rhine scale. And it is a length scale that I'm not going to delve into the details on, but it's something that governs wave vortex transition. Actually, I guess I will delve into the details in a little bit. The key thing is it's a length scale that, again, is a velocity. Now it's divided by beta, and it has a square root. So the key thing is this is a 1/f. This has a 1/beta with a square root. And since f and beta have different senses of how they change as you move poleward, they have an opposite direction. So the Rhine scale, this length scale, is something that is finite at the equator, and then it increases slowly and then increases very rapidly until it blows up at the pole. So we have one thing that goes down, and we have one thing that goes up. And there's these two length scales, and their interplay is very important for understanding this system. So what I want to highlight here is there's a critical latitude where these two length scales intersect. So, and so why does this matter? So just to give you some insight into this. So the idea here is that if you are a vortex, this is the length scale you'd ideally like to be, is this solid black line, this natural length scale. But if you are a lot smaller than this Rhine scale, what it says is basically that you don't really feel beta, and so you're very happy. If you're down here, that's what this length scale is telling you. Versus over here, if you're much larger than this Rhine scale, what it really means is that you feel beta very strongly. And another way to put this, and I'll show this in a little bit, is that you're going to generate Rossby waves. So there's basically two regimes in here. In this system that you can understand in terms of the interplay between these two length scales that are really fundamental to the rotation of our planet. Okay, so why does this matter? And so I'm kind of jumping a little bit to just give you some insight into the qualitative state of this funky tropical cyclone covered world. Is that what this theory can tell us is, so why do we have so many vortices at high latitudes? It's because beta gets really, really small. And so what that means, if beta is really small, is that vortices can just exist. They're not going to produce Rossby waves, and so they're just happy. And this is actually something you see on an F plane, where you have no beta at all, is that F planes just fill up with hurricanes, and they just last forever. And so that's essentially what we have at high latitudes in this regime. But we don't actually care about that regime. What we care about is here, in this cyclone sparse region, we actually implicitly have a mix of waves and vortices in here. So a mix of tropical cyclones, but it's a region that also will generate a lot of Rossby wave activity. And it's this region that, as I mentioned, that tropical cyclones follow trajectories that are not that different from the real world. They're just sort of, in the real world, tropical cyclone tracks, or tropical cyclones are confined longitudinally to certain regions. Whereas here, they can basically, there's no zonal preference at all. So this is to say that this region may actually be really, really interesting to understand our real Earth. So this is where hurricanes form on Earth. So maybe we can learn something about hurricanes on Earth with this wacky looking setup. Okay, so let's come back to our three questions. So again, we're interested in genesis rate and how far from the equator you can be, and then also storm size. And so we're going to walk through each of these one by one. And again, the original prevailing hypothesis, which I'll mention specifically, is they all depend on F. So what we can do now is take our wacky hurricane planet, our aquaplanet, and so when we talk about varying F and beta, or talk about dependencies on F or potentially beta, what really matters is that each of these F depends on the planetary rotation rate, and then beta depends on the planetary rotation rate and the size of the planet. So I should have said planetary rotation rate, omega, and then A is the radius of the planet. And so this is nice experimentally because we can vary these parameters, and in particular, if we vary the planetary radius, F does not depend on the planetary radius. So if something changes when we change A, then it must depend on something that's not F. In just like simple logical argument. So what we can do is take our planet and our Earth-like aquaplanet, which is here. This is the movie I had shown before, the control. And we can double the planetary rotation rate. We can have the planetary rotation rate. We can have it one more time. And then we can also start from the control and either double the planetary radius or have the planetary radius. And just keep in mind, these are not drawn to scale now. And so I'm not going to dwell on these other than to put tons of hurricanes on the screen at once, which is fun. And you can just stare at it. And you might get a sense by eye that clearly some things are changing. So, but we're going to step through quantitatively answering the questions I want to answer. But things change when you change all of these parameters. And so we'd like to be able to use this now. These are experimental testing grounds where we can really precisely test our hypotheses for each of these three questions that we talked about. So let's start with the first question is Genesis rate versus latitude. So the prevailing hypothesis for this is that this is something that should scale with F. And formally, this should be the absolute vorticity, but in what's nice in our aquaplanet is we don't have large-scale relative vorticity in the system, so we can really, really isolate, focus just on F, on the planetary vorticity. And this is something that's encoded in a lot of Genesis potential indices, for those of you who work with tropical cyclones, is that it's often just assumed, and like with empirical grounds, that Genesis scales with F. And so that's reasonable to think about even intuitively, but it's never really been formally tested. So what we can do is, we can look at Genesis rate. So this is a rate per unit area per time on the y-axis, and as a function of latitude on the x-axis. And so what's fun is, so we can start off, and brown is this control aquaplanet experiment. But we can, again, we're using the same model that we run the real world simulations in. So we can actually always do direct comparisons to the real world as well. And so that's shown in this blue. So clearly and you can think about it, in the real world, there's a significant suppression of Genesis relative to this control aquaplanet simulation. Genesis increases going up to something like 30 degrees north, and then it decreases from there. And then in this region, that's in that cyclone-filled cap where it's pretty hard to actually determine Genesis points in there. So we're not worried about that part of the planet. So that's just some context. In this case, the real world one is less important. So what we can do then is look now across our experiments where we vary planetary rotation rate, which is going to be in the browns, and then vary the planetary size, and that's going to be green and red. And so this is Genesis rate as a function of latitude, and it's just kind of a big mess, which is fine because by varying, say, the planetary rotation rate, we're also varying how F changes with latitude. And so what we'd like to do is to say, well, if our hypothesis is that it's F that matters, let's map this onto a function of F. So now the x-axis here is the Coriolis parameter. And so what's remarkable now is if you notice that there seems to be this sort of like quasi collapse across the different curves of how the rate at which Genesis increases with F across all of our simulations. And so you can approximate that. So this is just this black dashed line is just a linear increase. There's maybe some subtle nonlinearity there. It's not something we can really distinguish here. But we're getting this result that Genesis rate across these simulations really does increase almost quasi-linearly with F, which is pretty cool. So there's a slope. Why is this the slope? I have no idea. It seems to be something very intrinsic and fundamental. So about 0.7 with funky units. So the other part is, so they all increase, but they increase to different points. So that these dots are the max Genesis points. And what's remarkable is actually that this the value of f where the genesis peaks actually, and I don't have it on here, but scales quite nicely with a value of f at the critical latitude between those two length scales, the one that goes up and the one that goes down. So that's sort of like a more broader theoretical point, but it's consistent with this kind of two length scale theory that we're proposing. So, okay, so the first question is something that, again, has been, I'd say, known empirically for some time, but we've really tested it, and we're finding that it really, really does work in these simulations, which is awesome. That it scales, genesis rate in terms of the dynamics scales with really probably absolute vorticity, or say F in our simulation. Okay, so the second question we're interested in is, so we said we can't form on the equator, but how far from the equator do you need to be? And so this is something, I put a question mark at the end. The loose prevailing hypothesis is that maybe you need some minimum threshold value of F. You need enough background rotation to be able to draw on to form a hurricane in the first place, which is a reasonable thing to think. And so what we can do is to take all our simulations. So again, these are all of our aquaplanet simulations, varying planetary rotation rate or planetary size. And now what I'm plotting here on the x-axis is longitude. So we're getting a zonal view of where storms exist. And what I'm plotting is the minimum latitude within 5-degree bins of where storms exist in our simulations. And so the y-axis here is latitude, north or south. And then these stars here are the median of the curves. So they give you a summary statistic. And where you can see that this quantity seems to be varying across all experiments. So including varying the planetary radius, which means that we don't expect F to explain what's going on here. Let's see here. Okay, so the median latitude of each curve. And so what we can do then is we're interested in the distance from the equator. So across these different planets, there are different distances between, well, I should say for the varying the planetary radius, the distance from a particular latitude to the equator is also changing. So you're changing the size of the sphere. And so we can actually calculate the absolute distance from this point to the equator. And we're plotting this on the y-axis here. And then, so I mentioned, so since A seems to be changing this, the planetary radius seems to be changing this, it's F can't be what explains it. And so there's sort of the second simplest hypothesis is an equatorial Rhines or deformation scale. So it's this, it's the Rhine scale, but I've just plugged in phi equals 0, so you're at the equator. And we actually can't distinguish this from a traditional equatorial deformation scale because it's a scaling. But when you get plot that on the x-axis versus this distance, this minimum distance on the y-axis, and you get this really nice scaling across all of our experiments. And so what does that mean? So yeah, first, that's not a threshold value of F. And so one other thing is we can actually throw the real world on here. So this is this blue curve here. So now you're seeing there's more zonal variability. So right here, these longitudes, this is the maritime continent here. So this is actually where on Earth we see the lowest latitude hurricanes that form. They can form very close to the equator. In our model, there are storms that actually form at the equator. And that's because in the maritime region, we have large-scale relative vorticity that exists. And so that means, so that basically shifts southward how this region where storms are able to form. And so you have a deviation in the real-world simulation here from the scale. So what does this mean? So this length scale is really, as we'll talk about more, is more of a size scaling. So it's the physical implication is that you really need to fit most of the storm circulation on one side of the equator. So it's not about what the F is at the center of the storm, but it's that if you're going to have a storm, it's going to have some size length scale associated with it. And most of that needs to be, ultimately that's where angular momentum is being drawn into the center of the storm. And so that's the part that needs to be at least mostly on one side of the equator.
Can you repeat what U beta star is there?
U beta, it's U beta divided by 2 pi, I think. Yeah, it's a velocity scale. So this is a good point. So pick this to be constant because that's the easiest thing to do. And then actually I'll be talking about why you shouldn't be constant and how to think about this differently soon. But in this case, this is just a constant. So this is part of where I say it's just a scaling. Like the velocity is an arbitrary velocity choice, essentially, so we can't distinguish between some other velocity scale there. Okay, cool. So I think we have now a better answer for this question of how far from the equator do you need to be. There's this equatorial, again, they say deformation or Rhine scale, a scale that depends on beta at the equator. So the third question is storm size, and how does that vary with latitude? And so the prevailing hypothesis, which was the subject of my PhD dissertation, was that there's a length scale, that's a 1/f length scale, that should govern storm size. So I'm going to tell you why that's wrong. So this is the prevailing hypothesis up till now. So there's been a lot of work on this, and it's all been stuff on an F-plane, and so this is where now we're thinking about this on a sphere. So this is where I give you a little bit of context. When I talk about storm size, what do I mean? So a hurricane, so this is a radial profile of the rotating wind on the y-axis versus radius on the x-axis, and this is actually observed, or like observation-based data from a couple of data sources. This is from Hurricane Katrina in 2005. So the wind speeds tend to increase very rapidly to some point. This is our maximum wind speed in a hurricane. These are the categories 1, 2, 3, 4, 5 that we talk about in the news. But then winds decrease very rapidly from there and then more gradually. There's a relatively long tail in the outer wind field of the hurricane. But there is an outer edge to the hurricane wind field. So this is a wind profile for a hurricane, and this structure is fairly consistent across storms. It's a quite robust structure. And so as one definition of size, so I'm going to kind of people use different definitions, including myself, and it just varies from time to time. But the simplest one, if you ever hear the radius of gale force winds, so that's 17.5 meters per second, you go out here, here's your size metric if you're interested in the radius of 34 knot winds. So you can pick any wind radius you want. I'll use a couple of different ones here. It's not super important. Other than to say that I'm interested in something that's a measure of the outer size of the circulation. So it's an overall size of the storm. And so, so the key thing is, one important point is that storm size varies a lot in nature. So this is just a histogram of the radius of 17.5 meters per second from the extended best track data set in the Atlantic Ocean. And so you have a median here, this is about 156 kilometers, but there's a pretty wide standard deviation, and it's approximately log normally distributed. So we can have very big storms, like Hurricane Sandy was enormous. I think our 17.5 for Hurricane Sandy was like, I forgot, 1,500 kilometers or something. And then we can also have very small storms. So this varies a lot in nature. And so just as a note, why would we care about size is that bigger storms tend to produce greater hazards across the board. More storm surge, a larger footprint of wind, more rainfall as well. So it's just basic motivation for why we would care about storm size. And so in nature, size also tends to increase slowly with latitude statistically within the tropics. So this is latitude on the x-axis versus this radius of gales on the y-axis, and it increases gradually, especially at low latitudes, and then you get higher latitudes, you start to have extratropical transition, which tends to make storms become bigger faster. So this is how this is what we'd like to reproduce and understand. So I mentioned the prevailing hypothesis was that there's a 1/f scaling for storm size, and so this is going up slowly, and this is going down very fast. So it is definitely wrong. So definitely not that. Good PhD. I'm just kidding. There's lots of things we learned from that too. But so alternatively, there's this other length scale here, which is maybe the Rhine scale. And I actually will just emphasize for the students in the room, this is basically the process of how we figured these things out, was to not really know what we were doing and just being like, what is this? Maybe this is better. And then it took us a long time to really understand the things that I'm going to talk about next about the Rhine scale. So the point is we have a second hypothesis that seems like, at least qualitatively, maybe that looks more reasonable. So let's explore that. So I mentioned size increases slowly with latitude in observations. It does so in our so the blue, sorry, to focus on the center line, so this shows you the variance at any latitude, but just focus on the center line, is that storm size tends to be constant or increase slowly with latitude in our real world simulation. And then it also does so, at least to first order, in our aquaplanet simulation, so that's really nice. So these things are not inconsistent with what we see in observations, including in this crazy aquaplanet world.
Wait, so the AMIP, it looks like it doesn't? Is that?
No, I'm saying neither of them do this, and they both, at least broadly, consistently go. I'm not going to say these are exactly the same, because they certainly are not, but they both are either constant or slowly increasing with latitude. So, and then you'll note they diverge here very strongly. Here in the aquaplanet, storms get smaller at really high latitudes, and in the real world, again, they run into the jet stream, you have extratropical transition, and they actually get bigger and bigger from there. So this is a place where at high latitudes, clearly our aquaplanet has nothing to do with our real world. Okay, so first I can just put Orion scaling on here and say, well, that also looks pretty consistent, which is nice. So there's at least some sense that seems to be a better hypothesis here. So now we can actually test this, though, again, in our simulations, in our aquaplanet simulations, varying our parameters. So what does that look like? So on the left here, let me walk you through this. I have these pop up one at a time. So latitude again, this is now the radius of 2 meters per second, so we're really looking at the overall size of the hurricane here. And so the control again is in the brown, and so it'll highlight, let's see here. So, so this is varying the rotation rate, and then this is going to be varying planetary size. Let's start with this side. So you'll notice that these curves, so here these higher rotation rate going to lower rotation rate, size increases, and it increases at a very specific rate, which is about omega to the -1/2, which is consistent with the Rhine scaling. So slower rotation rate gives you a larger storm. And then over here, we have going from larger planet to smaller planet, or smaller planet to larger planet. We again have this systematic increase in storm size that scales with roughly a to the 1/2, which is again consistent that a larger planet gives you larger storms. So both of these things, these specific square root type scalings, are consistent with this Rhine scaling. So now we're really seeing that, yeah, this scaling, even if at this point we have no idea why, like what it means, but clearly the scaling is showing up here. So, and then at high latitudes, things do different things, which I'm not going to talk about here. So, cool. So for our third question, we have a new, better hypothesis, which is this Rhine scale. It seems to govern storm size, at least in low to mid latitudes, on probably our real planet, as well as in these aquaplanets. So we have kind of 3 questions that we've been able to come up with nice answers for that I think are fairly cleanly tested in our experiments. So that's our sphere. So now there's a second step. I've talked about this Rhine scale, and we're going to talk about this more. So now thinking about this question of hurricane size on the sphere. And so this is work that's led by my PhD student, Kwan Yu Liu, who's done some really awesome work on this, and this is work that's in press now, so you can look for it, or I'm happy to send it to you. So many of you may be thinking this, or maybe not. This was a question we got from a reviewer on our first paper. Why would a hurricane care about the Rhine scale? And so we spent in our paper a lot of time trying to explain it based on past work about this Rhine scale, which is a whole mess of really complicated theory that I still don't really fully understand, but it mostly comes from the baroclinic turbulence literature. But there is some interesting work on vortices on beta planes, but they're also super complicated. But so it all came back to saying that we really didn't feel like we could satisfactorily answer this question. We just gave them a whole bunch of references and tried to explain it, at least conceptually, what we thought was going on. And so then now we're going to do a little bit better than that, hopefully. So the Rhine scale is this thing that I feel like nobody teaches, but it comes from an incredibly basic equation, which is the barotropic vorticity equation. This says the tendency of relative vorticity is governed by 2 terms. There's a nonlinear advection term, the flow advecting the vorticity around, and then we call the beta term, where beta shows up. And what these are in super basic terms, is that this is a term that just sort of spins vorticity around, if you will, or moves it around. And this is the thing that makes Rossby waves. And so the Rhine scale is a scale, if you have a velocity, that governs when these two terms are equal to each other. Which is to say that if you're much smaller or larger than this length scale, it tells you that one of these two terms is negligible, and then the other one is important. So, it turns out, so if you do a scale analysis of these two terms, you can derive a Rhine scale, and you're going to get this length scale scales with the square root of a velocity divided by beta. And this u is not a wave phase speed, like a deformation radius. It's a resolved flow speed. It's the motion, the actual flow motion speed. And in all of the literature that I've ever seen from baroclinic turbulence world, it's always picked to be some characteristic flow velocity. The idea is that you have turbulent motions, and then stuff happens, and so there's some sort of a turbulent velocity built in from the atmosphere being stirred around. And so this is a constant velocity. And so in a tropical cyclone, though, we definitely know that the velocity is not constant, and instead it varies very strongly with radius. So, so I should mention, going back to Larissa, your question was that in our first paper, we just took this velocity to be constant, which is fine, but now we're trying to think about this a little bit differently. So in a tropical cyclone, u is definitely not constant. We know it varies very strongly with radius. We actually have a very good understanding of the physics that governs this radial structure. And so how do we think about that? So I'm going to step through this, and if this doesn't resonate because it's too quick, it's fine. But like you can derive, go back to the barotropic vorticity equation, derive the Rhine scale, basically what I had shown before, where this velocity, the problem is that this is something, because the velocity varies with radius, this is not like a single length scale. It's something that should vary with radius, which is not super helpful. But you can think about this in a different way and transform this, instead of in terms of a length scale, you can think about this in terms of a velocity, which we'll call the Rhine speed, which is something that now depends on beta and radius, which means it has, if you know your value of beta, whatever latitude you're at, this is a fixed dependence on radius. It's an invariant function of radius.
Radius of the storm, right?
The radial structure of a
So
hurricane allows
this
you
is
to do
like,
that?
what's that?
The radial structure of a hurricane allows you to do that? Or?
So no, so this is independent of anything. This just says, this, I'll show you in a second. This is just radius from the center of something. So this is a speed that depends on whatever beta is a constant, and then radius. And so what does that mean? So let me just show you this. So what does that mean is, here is a wind profile for a hurricane. Looks very similar to the one I showed before. It's a little bit different. And this is the Rhine speed. And so this is where I say it's a fixed function of radius, in that it does not depend on whatever the circulation wind speed is doing. It is just a background velocity scale in the system that happens to vary with radius. And so why is this interesting is, so we have a wind profile that decreases rapidly. We have this Rhine speed, which increases rapidly with radius. And there's an intersection point. Once again, we have a thing going up and a thing going down. So there's an intersection point, which we're just going to call the vortex Rhine scale. And so why do we call it that? So I'm going to call it RVRS. Is that the idea is that physically, inside of this vortex Rhine scale, the circulation speed is much faster than the Rhine speed, which just says that you don't feel beta. You're spinning so fast that you don't notice that F is changing over the length scale that you're spinning. And so if you have a circulation there, it's going to be happy. If you're outside of this, this length scale, this vortex Rhine scale, your circulation speed is significantly less than this Rhine speed, which means you're going slow enough that you're going to feel the effects of F changing over the trajectory that you follow, and you're going to generate Rossby waves. And Rossby waves move away and take energy with them. And so that's the critical aspect of thinking about this Rhine's effect in the context of an actual vortex.
Yeah.
So yes?
So in the expression for the Rhine speed,
Yes.
it goes like, it's proportional to beta. You chose beta as a constant.
In this case, yes.
But since beta does vary, Does that suggest some sort of refraction of?
Good question. I don't know. We are not thinking about variations in beta because it's already complicated enough with variations enough. So yeah, it's a good question. I don't know how that would change things or how that affects Rossby wave propagation in general. So we have to think about that. So.
Does it say something about that potential transition point though?
It does in a, yes, let me get to that in a second because I'm going to talk about that. Okay, so let's see here, got a little late. So let me, so I'm going to talk about this. So what we want to do is to test this theory, and so we're going to work with the simplest possible model. So this Rhine scale idea comes out of the barotropic vorticity equation. So let's run a model with that is literally just a simulation of the barotropic vorticity equation, a non-divergent barotropic beta plane model. And what we're going to do is stick in an idealized axisymmetric tropical cyclone. And so this is where I mentioned that the structure of tropical cyclones is very well understood. And so we have a model for the physics of that structure. So what happens when you do that? So I'm going to play this twice. So the colors are wind speed. And the time is up here. And I'll play it again so you can watch it again. So this is about a day a second. And then the red circle is the vortex Rhine scale at the start of the simulation. Do it one more time. So you start off with this broad wind field, and then if you'll notice, there's a circulation inside of here, and then there's a circulation outside, and the circulation inside persists for a very long time, and the circulation outside of it decays away over something like 10 days. And so what we're able to do is this is a prediction of the transition point between the part of the vortex that's happy and the part of the vortex that's going to radiate Rossby waves away. And that radiation of Rossby waves weakens that outer circulation over time. So this is a physical manifestation of what the Rhine scale is doing. Why would it limit storm size? And so I'm just going to show, so I'm not going to go through all of these. We do a couple sets of experiments where we can vary the initial storm size and keep beta constant, and then we can also vary beta, so this changes, we keep the circulation constant and we vary beta over different latitudes so that we have different Rhine speed profiles and see what happens. And so this is where I'm not going to go into all the detail. I'll show you one example, which is the simplest one, where when we vary the size of the storm, so the y-axis is the size divided by the vortex Rhine scale, so you're starting up here at like 5 times the vortex Rhine scale, and then track how the size changes in all of these experiments at different sizes. So these are bigger and smaller storms, all converge, and they converge to something that's just a little bit smaller than this vortex Rhine scale, so we can actually predict where they end up. Yeah?
Sorry to interrupt. So if you have this the outer winds are decreasing with time, I mean, you would eventually create an inertially unstable vortex. Is that part of it?
Yep, so that's not in here. The model doesn't reproduce that, but you're absolutely right, yeah. So that's one thing, is what the model produces is not a realistic looking vortex. It just shows you how this effect induced by beta would affect a tropical cyclone with nothing else going on. So, yeah, it's a great question. So anyways, so that's, we do other experiments. I'm not gonna go through all this. I wanna just show you a little bit of this sense. And a big takeaway from this, going back to your question, was, so for any of you who is familiar with baroclinic turbulence theory, it is often said the Rhine scale cuts off the inverse energy cascade, which is an incredibly complicated way to say that baroclinic eddies, extratropical cyclones, tend to expand with time until they reach their Rhine scale, and then they stop. And this is really the exact same physics. And we have couched it in the context of an individual vortex, and we've done it for a tropical cyclone, but there's not really any reason why it shouldn't apply to an asymmetric circulation like an extratropical cyclone. And it's really fully consistent with this huge bed of literature that I don't really fully understand from baroclinic turbulence theory. So this is something that actually is really probably much more general in understanding this Rhine scale and what it actually means than just for a tropical cyclone. Okay, so I'm just going to end with one last thing. That's a cool thing. I'm not going to show that. One slide is what does all this mean now for hurricane size in the future under climate change? So could storms get larger? We expect storms to become more intense. There's a lot of things that we expect to get worse with tropical cyclones. So this is some work led by Ben Schenkel, who's at OU, and this paper is in revision, and I'm just going to show you one slide from it, which is that what we find in climate models is that there is definitely no agreement on any significant changes in size versus latitude in the future. So this, just to hone you in here, this red line is no change, and this is percent changes in storm size. And obviously, any individual model, there may be some changes, but they just put up here two models, one that shows slight decreases and one that shows slight increases, at least at lower latitudes as a function of storm size as a function of latitude. And this is something that's very consistent with this Rhine scale. That this is a dynamical planetary effect that it's effectively thermodynamically invariant. And so it says that if you warm the planet, this process is still here. It depends mostly on the planetary, on beta, which is a feature of the rotation rate of our planet, the size of our planet. So that's just nice. This is like, for once, maybe good sign. I will say this is only as a function of latitude. You could definitely have regional variations. This is what the colors are here showing. But maybe it's a good thing for once. We have something that we might expect storms won't get bigger in the future. So yeah. So that's, let's see here. There we go. Okay, so I'm just going to end with a very high level thing, which is just Earth is complicated. I hope, try to convey for those of you who don't even care about tropical cyclones, a way in which I think about these problems and how to use computer models as kind of experimental tools to deconstruct our world. So I think of these as we have real worlds. We can make imaginary worlds, which is really awesome in computer models. To understand and explain and even better predict tropical cyclones on Earth. So yeah, the big takeaway, I guess, is that size seems to be very strongly constrained by the spherical geometry of our planet. So yeah, here's some papers. Thank you all. Thanks for having me. Thanks for listening.
You never said much about environmental data associated with
Large-scale vorticity.
long-term vorticity.
Yes. So that's where, absolutely. And that's where things like if the structure of the jet stream changes, you could definitely have large-scale changes in the gradients of relative vorticity. And so at least from the climate models, looking at what we're seeing, like it doesn't seem like that's a huge factor. I mean, I know the jet stream structure will change. I think the other question actually is when I talk about this, we're thinking about the circulation of the tropical cyclones confined to the lower troposphere, in which case the jet stream, that means a lot higher up. But yeah, long story short, I mean, absolutely, that could play a role. At least to first order is probably not as important. So.
I think we usually try to answer the student questions.
Oh, yes. All right,
first.
cool.
So Karma had a question.
Yes.
Yeah, I don't know if this question makes sense at all, but it's just related to how we can use this to understand the intensity of the cyclone and how, I forgot the last part of the question. Well, how we can use this to understand the intensity of the cyclone, to know at what extent it depends on the dynamical feature instead of the thermodynamically conditions or something like that.
Yeah, so for intensity, so I think the simplest thing is, so intensity and size are largely independent of each other. You can have large, weak cyclones, tropical cyclones, large, intense ones, small, weak, small, intense. So in terms of the size part, it's not very much insight into intensity. That's not to say there isn't a relationship there. Are you asking kind of more generally about how to use these types of models to understand intensity, or?
Were you asking about intensity or density?
Intensity, yeah.
Intensity, okay, yeah.
Yeah, what about intensity rate of change?
Rate of change, yeah.
That might be more related.
Yes, so this is where, so my colleague Kevin Reed has since done work looking at where they take this aquaplanet setup and then change the global surface temperature and look at how intensity, which goes back to what you had said, intensity change, precipitation, things like that change. And so this same setup, you can use that and you also get increases in intensity, increases in intensification rates, increases in precipitation, all of those things come along with it. So yeah, does that answer your question? Yeah, cool. Yeah, so it's an awesome setup for that. So I didn't focus on that. But it's also a wonderful place to be able to test thermodynamics as well. So, yes, we have more. Hold on,
Do we
yeah,
have
yes,
any
back
more
there, sorry.
questions? Camille?
Yeah.
Yeah, so if they go to the intersection of the lines.
Sure, let's see. Where are we? This one. Here?
No, the one that varies with radius. and-
Oh, yes. Yeah, here, I got you. This one.
Yes. That's it, yeah. So are you saying that if the storm starts off that has a greater, better shape, would have a larger vortex line scale? So if the wave profile is much wider than this, then the line scale would go outwards as well.
Yeah, like if
So
you move like
it
this.
would maintain its scale, its length, or its radius much better.
Yes. Yes, this is what my student is now working on, is yes. The implication is that, I guess, if I'm understanding it correctly, yeah. So if you move this profile outwards, you're going to shift where the intersection point is farther out. That's what you're saying?
Yeah.
Yeah, and I think a way to think about it is what's in here is protected dynamically. And so, yeah, that's where the wind profile can have an impact on the radius over which it can last longer, essentially. So, that's what you're asking?
Yeah, and does that imply how a storm can intensify, and also how the intensification depending on how the storm wave profile starts?
That's a good question. Not in an obvious way to me, but I mean, I think it could matter. I mean, it's going to, this effect of, like, what I would say, like this process affects the angular momentum structure. And so ultimately the winds being strong here because angular momentum has been brought to smaller radii. And so changing the wind structure and the angular momentum structure at intermediate radii alone can have an impact on angular momentum fluxes inwards. But then it also may project onto how much this Rossby wave effect can effectively like eat away at the wind profile. So it's sort of like a hand wavy answer to be like, it's possible, but I don't know that the way we think about intensification right now, it's totally obvious how that would work other than like transient effects on angular momentum transport inwards. So yeah, so maybe, that's what I'd say. Yeah.
Yeah, I've always thought that the line scale was really cool, but mysterious and impenetrable.
Mysterious.
So I don't think I really get the depth and profundity of it, but you have added a new meaning to it.
Thanks. I will say my student came up with this, and I did not believe him for a while. And then he persisted, and then now I am very grateful. Because I was like, you're wrong, and then eventually I was like, oh, I get it now. So thanks.
At the beginning, you had a really elegant approach of, well, this all was, but here you explored F and A. What about the other branch of logic? Would it be worthwhile to think about rotating cylinder on that plane and put stripes of temperature patterns and look at, how does the meridional and Atlantic meridional node affect hurricanes? It seems like there's this interdecadal variation in number of hurricanes in the Atlantic too. So people say that.
Right.
Are there idealized experiments that support such a thing?
Okay, there's two separate things there. The cylinder thing would be awesome. So actually, if you're on a cylinder, then you're basically at the equator at all time, everywhere. So you would never have any projection of the planet's rotation. So you'd probably not have any hurricanes on the cylinder. If you have a cone, though, yeah, cone. Yeah. So I've thought about this. It would be awesome. I don't know. This is where we work with the existing set of climate models that simulate the real world. So maybe there's someone out there who's done it, or you could try to write a conical GCM, which would be cool, but I don't know. So the short answer is yeah, totally, and it would be cool, and you could probably do some other cool experiments.
No conical exoplanets. Are you going to do exoplanets?
So we have done exoplanets. Yes, actually, we've looked at whether exoplanets could have hurricanes. So tidal elect exoplanets, but they're still spheres. because the exoplanet people also, I'm pretty sure, I don't know, the space people, but I'm pretty sure planets like to be spheres. I think it's really hard to create a cone planet, if I'm not mistaken, that have atmospheres. I'm pretty sure my space colleagues told me that, like, if you're going to have a planet that's massive enough to have an atmosphere, it's also probably going to be a sphere because of physics stuff. So I don't quite know. Second question, the Atlantic Meridional Mode. Yeah, I mean, I'm sure would be some cool idealized experiments you could come up with for that. So I don't know. I'd have to think about that more. But yeah. Definitely. Yes, back there first.
Yeah, this is a somewhat related question, but this is the first time I've ever seen like a thermally equal everywhere aqua planet, and you seem to have gotten a lot of really cool insights about the dynamics here. So I think in my head the obvious next step is if you just put normal insulation on it, what can you learn about the interplay between dynamic and thermodynamic constraints?
Yeah.
As people on that.
Yeah, great question. So there actually has been work by Bill Boos and his group a few years ago where they did this on a beta plane, and they started from no temperature gradient and applied a temperature gradient systematically stronger and stronger, and saw how it responded. Which is just to say that, like, we could do that here, but I think we'll end up seeing the same thing they saw. So yeah, and what you end up with is, like, for even like a relatively weak temperature gradient, you pretty rapidly shut down tropical cyclones at high latitudes. Yeah, like that polar cap, you can lose pretty quickly. So yeah, so it's an awesome idea. And you get, like, basically, you'll end up, if you put a reasonable temperature gradient, you'll end up with something that looks somewhat like Earth, where they're mostly in low latitudes. Yeah, sorry.
Kind of along those same lines, I don't know if I missed it. Was there a diurnal cycle in your simulations?
There was, but it doesn't really do anything. So that was honestly just, we hadn't thought about it, and we still had a diurnal cycle on. So we technically say that diurnal mean is constant everywhere. But since the sea surface temperature is a constant, it doesn't mean there's not an effect at all. Like, we do know that diurnal solar absorption, like, does seem to matter. There's a signal of that in real tropical cyclones. So, but I think we had done a test where we turned it off and didn't really change anything. So it's probably not important. So yeah, Betsy, you've had your hand up for a while.
Yeah, I just can't see behind you, so I didn't know who was going to ask the question. Really excellent talk, Dan. I wonder if, and maybe it's related a little bit to Noah's question, is the slope from the VRS to the center of the hurricane going to be constant in the circulation wind speed, do you think? So that it does matter what the scale of the storm is for its maximum wind speed?
Is the slope of...
The slope of the brown line from that intersection point to zero.
Oh, to here.
Yeah, have you?
Yes, absolutely. Yes, I mean, I would say, the way I would put it is that the thing that I didn't really say is, I mean, this is, what we're really saying here is that the farther out you go, the more Rossby waves, there's a greater eddy flux of angular, of momentum, just linear momentum if you want, out of the system by Rossby waves. And so this is not a wall. This is not a yes, no. In reality, there's a transition. And so the closer, so yeah, this is something my student is and this is his current research, is understanding what about, like, if this gets pretty close here, you can think about it like there's going to be a wave-induced flux of momentum out, and that is essentially a sink of intensity, if you will. And so, yeah, no, absolutely. So I think what he's shown so far is that as long as you're not super close to this, like this actually does, it's not a wall, but like it's actually a pretty good predictor. And as long as you're not too close to this, then you're very happy for a long time.
So the wider that radius is, the more well protected is the core of the vortex.
Yeah.
So it's like insulation against the environment that wants to kill it.
Yeah, like a dynamical, like an environmental dynamical something that's trying to break through the castle.
Okay, thanks.
Yeah. Yes, sir.
As the TC's developing, how does that that line intersect, and whether or not the genesis is actually going to occur versus being maintained once it's a well-established vortex?
Excellent question. My student will hopefully have more information on that soon. We're pretty sure this is really important for genesis. So, and like part of this idea is that the structure of the seeds that form cyclones may matter a lot. Because if you tried to have some sort of sea disturbance that was very, very big, it would just be ripped apart by Washington's energy. Rossby waves would weaken it very rapidly. So, yeah, so it's an excellent question. Yes?
So, one way to view the tropical cyclone, not in the lower troposphere, but the full tropical cyclone, is it's two pieces, right? It's a column of vorticity that extends to the greatest magnitude of the surface, but then it's surmounted by this lens of another vortex, which is an anticyclonic vortex that's produced through the latent heat release. How does this theory say something about the size of the larger scale anticyclonic vortex that surmounts the TC itself?
That's a great question. I don't know. I don't know.
That can also radiate out.
Yeah. I mean, you have a large, slow circulation, which ought to, I mean, I guess the point is that, yeah, I don't know, that's a good question, because like, I guess I think the process would still be going on. I mean, often, I guess outflow is often asymmetric anyways, so that's part of where I don't quite know, like maybe you don't see it because most of the time you get outflow jets or other things like that, but yeah, I mean, in principle, this ought to still apply unless there's some other reason that your outflow actually doesn't have any vorticity gradient at all somehow. I don't know. Yeah.
I'm wondering if you look at the simulations people have done of TCs in a quiescent environment without any jets.
Yeah.
Could this also speak to some of the dynamics that they're seeing?
Yeah.
That the outflow is constrained somehow by this mechanism.
Yeah. I don't know that it would constrain the outflow. I actually think it would. Actually, I don't really know. I mean, it would still weaken circulations because it's still an eddy momentum flux out. So I don't know that it would constrain anything. I guess it would just, I don't know what it means to weaken the outflow if you'd had like an idealizing cyclone. I mean, it actually makes me also think like that's where, those are on large enough scales where variations of beta with latitude actually might matter. You might have asymmetries across the outflow. I don't know. Yeah, it's a really good question. It's not totally obvious to me that it should matter, but I don't have a simple sense of why it would. So, yeah. Let me go back here. Yes.
So I think this is fascinating result, and I really enjoyed your talk. I've been kind of like thinking about this more in like how we can, like how I can like teach this to students, for example. And a question that I could have is like, well, you know, we're looking at the barotropic vorticity equation. Real hurricanes are baroclinic and have very large temperature anomalies. And my intuition tells me that these results are still applicable because in reality, you would just think about it in terms of PV instead. And then you would kind of get a similar scaling nonetheless. I just am curious about what your thoughts would be on the matter on like how this would scale for realistic hurricanes in which temperature anomalies are there and there's friction and all these other things that could come into the scaling.
Yeah, thanks, Al. That's great. I actually like that. I've never thought of it that way, but just saying, if you think about it as PV, it is like a barotropic, like a quasi-barotropic vortex. Because yeah, we've gotten this question a lot. Like actually this two length scale theory, I should have said, I realized I didn't say this. Like we made it up, and then it turns out the oceanography people had already done this, and they had thought about this in a barotropic framework. So it's like, this two length scale idea, yeah, it sort of says it works, it seems to work really well, and it just assumes that the whole atmosphere, at least this aquaplanet atmosphere in particular, behaves like a barotropic fluid. And so like tropical cyclones, which are fundamentally baroclinic, are somehow like a barotropic, act like a barotropic vortex. And I think actually, yeah, the way you said it is nice, is that's one way if you think about it from PV. Otherwise, I mean, I guess the other way I think about it is just that, like, it's sort of like the tropics everywhere on the planet, and so you often think of like what's the term for it? Like you guys know this better. Like you have the vertical profiles. You have only deep convection mostly in this atmosphere. Your vertical profiles of quantities like vertical velocity are sort of just like a simple curve, and so somehow that, even though like yes, there's a temperature gradient with the hurricane, it's sort of like that's just intrinsic to the balance dynamics of the hurricane, but like it's not fundamental to the rest of the system. So maybe that's what I'd say. I don't know. That's an awesome question, though. Yeah. So, yes, Jim. Oh,
Yeah, great talk, Dan, thanks a lot. Sort of a blue sky idea, but,
Yeah.
and it kind of circles back to my earlier question. It seems like if you imagine a rapidly intensifying vortex, hurricane, the limit of that slope, the limit of that curve is basically 1 over R, right?
Sure,
That would-
for
if you ignore
inertia
that.
stability.
Yeah,
Yeah.
so you conserve absolute momentum, exactly. Now, that means that your Rhine scale moves inward.
Maybe, if that happens, it depends. Like, I would say, what you say about intensification, I think of that as happening very much inside of this still. I don't know. This is generally the outer, kind of broader outer circulation. It's not to say it doesn't play in, but,
Okay.
so maybe I should say, flip it around. That's possible. I would think my first instinct is that intensification processes, I don't know, I mean, maybe I should be careful. If it was a weaker hurricane to begin with, let me go back to you. Keep going.
No, I think your point's well taken, yeah. And maybe you're right, maybe for genesis that's more important.
Yeah.
And maybe for the more intense mature vortices, you get a lot of mixing that happens, whether it's through inertial instability or barotropic, but it seems like it's sort of confined in on that, which might pull you.
Yeah. But,
I was fishing for something, but I don't think that's right, because I was thinking that if you're shedding off this energy, that could be a dynamical explanation for the secondary eye wall formation or something like that.
Yeah.
But it's a little too far out.
Yeah. No. It's good. Yeah. Like it.
Okay, well. Can we end with the day after tomorrow?
Sure, I don't care. I'm just here until we go to dinner. So I can stay all day.
We'll do one more question, Matt.
I'm just curious about the movie The Day After Tomorrow. At the end, a cyclone occupies all of the northern hemisphere.
Oh, yeah,
Is there
right.
a support or disapproval?
Probably refutes them. Probably.
And that's a great way to end that.
But
Okay, thank you very much for a wonderful talk.
Thanks.
thanks for coming.